And
surface map.
yeah, surface map. So what I would look at on this surface map is there's a major storm system in the center part of the U.S. With a low cold front coming out of Missouri, out of this low out of Missouri. There's another weaker front down to the south, stationary front running from northern Missouri all the way through Virginia out into the ocean. We have a warm front back here on the Rockies. Now this is typical of a cold front coming down from the north and stacking up against the mountains. It sits there for several days, and then the air starts to descend. When it descends, it warms, and it comes back as a warm front. So that's what you're seeing here. And we have another cold front off the coast with all kinds of rain associated with it. Over here in the Pacific, we have a maritime, this looks like a maritime polar air mass. Okay, here we have a continental polar air mass with this high pressure here. Down here is the Bermuda High, which is a maritime tropical air mass. Maritime tropical is providing the moisture that's feeding this system right here. Okay. So you can see the green is rain, the purple is snow and ice, and the blue is rain. Okay? So that's what I would say pretty much about that chart. That gives you a current position for the cold front and the low over the top of us. Okay, let's go back to that front. And now what I want to do is take a look at 500 millibar chart, because I want to see where that system is going to go. So we said the low is over Missouri. Notice that we've got a deep, deep trough here in the western part of the U.S. All the bad weather is associated with the divergence. See the divergence aloft right here? It's pulling the air up from down below. Remember we had that maritime tropical air mass here, spinning the moisture up. The moisture comes up, the divergence pulls it up. Okay, so that's why we've got rain here now. Yes?
I was looking at this yesterday, and are those the lines for like the wind, or is that something different?
These lines are, these black lines are what they call isobars.
Yeah.
And that tells you what the height of the 500 millibar pressure level is.
Okay, so that's not like...
It's not, well, the winds blow parallel to the isobars, but closer the lines are together, the faster the wind.
The faster.
Okay, that's what I'm saying. And then, see how the bars are pretty far away from each other there, but it was pretty windy yesterday, like when I was looking at it, like...
That's today.
Right into,
I know that's today, but yesterday it was, they're far apart, and, no, here, like, yesterday was pretty windy. I was outside all day and it was pretty windy. But on that map, the lines aren't that close to each other, so I was just kind of, you know what I'm saying?
Yeah, I would look at it, see there's divergence here, so the wind would be dying down in this region. It's converging here, so the wind is getting faster down here. It's diverging here, so the wind would be dying off.
Yeah, no, that's what
It's converging over here, so the wind speed would be
But like where we are, on that
It's
map,
dying off.
It was kind of windy yesterday, and it wasn't really
On the map.
on the map.
On the map.
It's kind of, it says it's really not supposed to be that way. You know what I'm saying? Like here, what?
What time?
Yeah, where was this trough line? Was it still here, or was it back a ways? Was the trough as deep?
I don't know. I got it on my PowerPoint.
Because
that I was
if
supposed to
it
do.
wasn't as deep, then that means that these lines, or these close together lines, were further north.
Okay.
I mean, it just all depends on where the system is. But in any case, you can see that system that was on the surface map, the front coming in off the coast. You can see strong divergence in this region here, pulling the air up from down below, pulling the moisture up from down below. So we've got weather there. We've got weather right here. A very deep, deep trough right here. Eventually, if this heads south, eventually this will close off and end up with a closed bowl.
What do you mean?
Okay? That's probably about all.
You said those isobars mean like the pressure, right?
The isobars mean the height of that particular level. So, for example,
as long as you have memory.
the pressure is right over here at the right, and you put a 0 at the end of it. This is like 5660, so at that particular station, the height of the 500 millibar pressure level is at 5,660 meters. Which means that at this location here, the 500 millibar level is here. At this location here, the 500 millibar level is a lot lower because this is a trough, this is a closed low, so the 500 millibar level is here. So you would end up with it coming down like this and eventually coming back up again.
Yeah. So that means high pressure?
This is a low right here.
That's low. What up top where you first were talking about was high
Here's a
pressure?
ridge, here's high pressure right here.
Alright.
Here's a low pressure right here.
Okay.
Okay, we've got kind of a semi-ridge right here.
We say okay, but.
Okay?
Yeah.
Okay, so that was the 500. Let's go to the
SQT.
SQT, no, I don't want to go to
250.
SQT, I want to go to
250.
250 millibar chart. And
Oh my.
what I want you to see is the jet stream. Okay, we have two jets. We have a subtropical jet right down here.
We don't need this much, we do it.
And we have a polar
We don't
jet
need this
up
one
here.
in our paper.
It's up to the top,
We don't need
down
this one in
like
our
this,
paper?
Swings all the way up.
No,
Max wind
you don't need
band
this in
right
your
into
paper.
here, okay?
I'm talking to myself on video.
And you'll notice how close these are getting together. This may eventually pinch off, and eventually we'll have something coming across like that, and the pole's low down here, but that's to be seen yet. In any case, where the red is, that's where the max wind is. Okay, so here's Missouri. The low in Missouri is right here. Okay, the 500 millibar low was back here, and then the 250 millibar low is right here. So what we've got is a negative stacking of the lows. When you have a negative stacking, we haven't talked about this in class yet. If this is the surface, and the low is here, and this is 500 millibars, and the low is here, and this is 250, and the low is here, you have a negative tilt to the axis of the pressure centers. That's a strong, strong system, okay? Because when you look at that, what happens is, if this is the surface, here's the cold front, here's the warm front, okay? That surface at 500 millibars, okay? Here's the low back here, okay? Notice the divergence over the top of the surface low, pulling that moisture up from down below, pulling the air up from down below. Okay, that's a strong, strong system. Okay, that's deepening. And if the jet stream is even further back, that makes it even a stronger system. Okay, let's take a look at it from a different perspective. Here's our surface low. Here's our cold front. Here's our warm front. Okay. Now, here's our low right here. The divergence is way, way out ahead of the system. It's convergence back here. So what happens when you have convergence aloft? What does the air do?
Down.
It sinks. So when it sinks, what's it going to do to this surface low? It's going to fill it. Yeah. So you're going to, this is a weak system, it's actually a dying system. Okay? So this is the kind of thing that you want for a system that's going to gain strength. Okay. So now we want to go to the
Okay.
Yeah. Which one do you use? The
I'm going to
Springfield?
use Springfield, Missouri.
Alright.
So you go to the middle,
I go where?
you go to the millibar chart.
I just, the millibar charts are right here in the upper air, and the SQT is right here. Okay?
I think that's the one I used.
And you can't blow that up any bigger.
I didn't do this right on my test.
No, you can't do that. Okay, so when we look at this QT, some of the things that we want to look at is, remember we said where the temperature goes isothermal aloft, that's where the tropal pause is. So you can see right in here, the temperature's basically gone isothermal. Okay, it's decreasing with altitude here. So right in this region here, tropopause is here. Troposphere is down here. Okay, first thing you want to look at. The next thing you want to look at is, where's the LCL? The LCL is right here. What did we say the LCL was? Bottom of what? The clouds, yeah, what else is it? Saturation, where temperature is equal to dew point, right? Absolutely. and the relative humidity is 100%. Okay. So here's the LCL across this line right here. Other things that you want to pay attention to are these blue lines that are going along in this direction are temperature lines. They're in centigrade. Here's 0, -10, -20, -10, -20, -30, -40, -50, -60. Okay? And it increases here 0, 10, 20, 30, and 40. Okay? So those are the temperature lines. The dashed red lines going up in this direction are the dry adiabats. Okay? In other words, the temperature is decreasing with altitude at 10 degrees centigrade per kilometer. The green ones that hook up over the top are the moist adiabats. In other words, the temperature decreases with altitude at 6 degrees centigrade per kilometer. Okay? So now the question is, well, how do I look at all of this? Remember, we also said that from surface to 800 millibars in this region here, it's all low clouds.
Yeah.
From 800 to 500, it's all mid clouds. And above 500, it's all high clouds. And the other thing we said is the temperature dew point spread of 5 degrees or less is probably a cloud. So the red line is the temperature, the green line is the dew point. So right in this region here, since this is above 500 millibars, I would say we've got some cirrus clouds out there. Okay? And we've probably got some up here. That's kind of high to have clouds, but the fact is, it's pretty close together. So cirrus there.
Oh, so close togetherness
Cirrus there.
shows that they're,
Yeah.
okay.
Yeah.
Shows what?
That
Okay.
they're clouds.
Now we come down to the mid-level, okay, 800 to 500 in this region right here. Notice that the green line veers sharply to the left, okay? That means that this is extremely dry. It's a flat top cloud, and it's going to be extremely dry in here. So if it's a mid-cloud, the best I can say would be something like altostratus. Be flat or layered. It would be alpocumulus. Alpocumulus is kind of puffy. And stratus is flat or layered. Okay? And then down here in the lower layer, notice that the green line and the red line are touching one another. Its relative humidity is 100%. And since it covers this whole layer, it starts down here in the low level and goes up into the mid level, this is probably nimbostratus. Okay. Anytime you have a really crappy day out there today, it's nimbostratus, yes.
If the green line passes the red line, does that mean it's unbalanced?
Underwater.
What?
If the green line is to the right of the red line, you're underwater. Okay.
Fish better start respreading the cook again.
How do I know it's Strata-Q? Well, this is not Strata-Q, this is nimbostratus. If it were Strata-Q, you would see that in the lower layer, the lines close together.
That means at 100,
The dew point would do this.
100%?
That would
if
tell
they're
you
touching.
Strata-Q.
Yeah, 100% what?
Okay,
humidity.
so we need to figure out stability. So how do we figure stability? Well, we've got to lift the air from the top of the inversion. And I want to see what the inversion is. Is that the surface? Yeah, there's a little bit of a layer there. I wouldn't take it from the surface, it's just a little itty bitty part right here. I would take it from right here, the top of this inversion, okay? I would follow it up dry to the LCL, which is this blue line here, so I'm gonna follow these two red lines parallel up to there. And then I would follow the green lines, and you can see where the green lines are gonna come. I'm gonna come over here on this side, and when I get up to about 500 millibars, the temperature of the parcel right there is, that's 10, 20, 2, 4, 6, looks like about minus 28. No. Yeah. I'm following, here's 0, I'm following it all the way up to here. It's, there's 0, here is 10, so it's minus 8 parcel. 500 millibar is over here, and it is at minus 12. Is minus 12 colder or warmer than minus 8?
Colder.
Okay, so that means the parcel is warmer than the environment. So what's going to happen to the parcel when the helicopter lets go of it? It's going to go up. So that means it's going to continue on up this way. Are we gonna have thunderstorms out here today?
Yeah.
Yeah.
The atmosphere is unstable. Right. So that's typical with an unstable atmosphere.
How do you tell if it's unstable or not?
Well,
Again?
we followed from this point here
Yeah.
up to here, and then we went up moist from there. And at this point, we crossed over from the left side of the red line to the right side of the right line. And when I follow it up, I'm always to the right of the right line. That means that the parcel is always warmer than the environment.
Is that the green, that
So therefore
light
it's
green
unstable.
line?
Yeah, this green dashed line.
Yeah.
But it's to the right of, if you follow it up, if the red line's.
So the chances of having a thunderstorm out there are great.
Means unstable.
In fact, this afternoon they've got, well, let's take a look at Springfield, Illinois. Just out of
Which one is
curiosity. This is southwest of us, and that's where everything is coming in from. So let's look at Springfield, Illinois, and they've pretty much got the same thing, okay? You follow it up, you get the top of the inversion, you follow it dry to the LCL, I'm gonna follow this red line right up to there. Here's the LCL, and now I'm gonna come up moist from there above, and I'm always to the right of the red line, so we've got an unstable atmosphere in Springfield, Illinois. Okay? Does that make sense?
Yeah, a little bit.
The reason for doing this is I want you to get comfortable with the interpretation, because that's what you need to do for your cloud project.
Do you have any questions?
I don't, do you?
No, if we do, when we're writing paper, well, is
Yes,
it
you
good
can
to
ask
email
me.
you?
You can ask me. Yep, I had several people bring their paper in, and I don't know how to look at that. So we spent a few weeks going over it.
That or we can come to your office.
That's what I need to
Yep,
do.
I'm down at Harmon 143.
Harmon 143. I have it on tape.
Give it on tape.
Is it okay if
Yeah.
you can have the chart to
Okay, give me there.
The charts are the surface map, the skew T, and the 500. And the reason I look at the 500 rollbar chart is, I want, if you're telling me it's frontal, I want to see fronts on your surface map. Okay. The reason I look at the skew T is, I want to make sure that you and I agree on what level your clouds are at. Okay.
Can we throw in a 250 mil bar?
You can throw in anything you want, but you gotta tell me how it supports your cloud. You just don't stuff a thing in there and not say anything about it.
Dang it.
Like padding the paper, if you will. You know. I look at the
I'm gonna
500
erase that
rollbar chart
part.
because I wanna see if there's divergence allowed. Now, the 250 becomes good if you've got cirrus clouds out there, okay?
I have these clouds.
Let me show you why. Okay, if I have, here's the 500, and here's the 250.
And the O-straps.
It's entirely possible that I've got convergence at the 500 millibar level, and I could have divergence at the 250 level. What's that gonna do to the air in between here?
To make it glide.
Yeah, it's gonna pull it up. And when it pulls it up, guess what happens? Cool, condense, and form clouds. Well, if you've got cirrus out there, you want to consider using a higher level chart. That's because of this right here. Okay. Well, we just gobbled up a whole 45